Oh, thank you very much. So just in case you can't tell, because the contrast is really awful on the screen, this is an empty tub of Vegemite. And this is a problem, because I really love Vegemite. And I ran out literally the morning before we got on the flight to come here. So this was good timing, guys. All right, so thank you all for coming. I know the AC has been a little flaky, but hopefully we can get it back on. Thank you all again for coming to this wonderful conference. This is by far my favorite open source conference, and it's an absolute joy to be able to speak here again. I'm just curious, how many of you have never heard me speak in person before? Oh, that is fantastic. This is gonna be great. So many new faces. All right, so for those of you who have heard me speak before, it's likely been on subjects ranging from creating new courses for TuxRacer to open source animation to my personal experience as a teenager in the open source space. And I come to you today with something completely different still. We will start with a quick background on who I am, and then we'll spend the first part of the talk walking through the fundamentals of pulsar astronomy. And then we'll talk about some of the open source software that makes that research possible. And then we'll have to take a short aside for the obligatory personal anecdote. And then we'll finish with how free software philosophy actually does play a significant role in the astrophysics community. So, who am I? I have been a user of open source for almost a decade. When I realized this the other day, it made me feel really old. I've been a user of open source since I asked my father one afternoon why my computer wasn't working, why it had a dark screen. And the story goes, I don't actually remember this, that he told me the reason was that I was using Windows. And then I replied by sighing and asking him to help me anyway. I installed Debian on my first machine at age 9 and started speaking at open source conferences, starting with LCA in Canberra in 2005. Most recently, I joined the Pulsar Astronomy Research Lab at Oberlin College, where I'm doing my current undergraduate studies. About a year ago. Thank you for the applause. And since then I've become an undergraduate researcher with Nanograph, which we will talk about shortly. So, in accordance with the obligatory personal anecdote, I have a couple of photos. Oh, that really is bad. Because they're kind of adorable. All right, so remember I told you about the whole age 9 Debian installing machine thing? Yeah, Dad was prescient enough to get some photographic evidence of that. For those of you who are curious or interested, that is raf.debian.org.
You were only 7 when that photo was taken.
Okay, I stand corrected. So I was fortunate enough to join the research team a few months before we took a trip to the Arecibo Observatory in Puerto Rico for a Pulsar conference. The man in this photo is my friend from the amateur radio community, Joe Taylor. And the reason he was at the Pulsar conference is he is the co-discoverer of the binary pulsar, which earned him a Nobel Prize. Hooray! Okay, so, and then a much more recent photo. This past summer, I went to a 2-week intensive summer school pulsar research program that was sponsored by the organization I indirectly work for. And one of the afternoon activities was a trip to the Green Bank Telescope in West Virginia. You'll notice a theme here of me with radio telescopes, Arecibo, Green Bank, and next week, parks. These are the 3 main sources of the radio data that my team and our umbrella organization use in our research. So yeah, next week Dad and I are going to go do some sightseeing and make sure I have the necessary photo to finish that triage. All right, so time to get to the good stuff. Okay, another question. Just curious, how many of you have heard of gravitational waves or gravitational wave? No, seriously? Oh, this is awesome. All right, I was not expecting that. This is fantastic. So this might be a little bit of a review for you. But gravitational wave astronomy is an emerging branch of observational astronomy which aims to use gravitational waves in order to directly prove Einstein's theory of general relativity. And this would give us tons of data about objects such as neutron stars, black holes, supernovae explosions, and about the early universe. So what are these elusive gravitational waves that we have yet to discover? They are minute distortions in space-time predicted by Einstein's theory of general relativity. So imagine a pond, the surface of which is very still. Don't laugh at me, Paul. The surface of which is very still. So imagine that as the fabric of space-time. Now imagine dropping a rock on the surface. But as we know, it has to be a very small rock because only very small rocks float. I was wondering how long that was going to take. So what happens? You get ripples emanating from the event that is dropping the rock into the fabric of space-time, the surface of the water. Those ripples are gravitational waves. However, to date, we have never directly detected them. So how do we go about finding them? Because it'd be kind of awesome if we did. We use pulsars. Pulsars are neutron stars that are formed when the core of a massive star is compressed during a supernova, which collapses, therefore, into a neutron star. The neutron star retains most of its angular momentum, and since it's much smaller than the original star, it has a much smaller radius. It has a very high rotation speed. It starts spinning really fast. So imagine something the size of 2 Wellingtons fit into something about half the size of Wellington, spinning at the rate of your kitchen blender. That's a pretty accurate picture of a pulsar. So a beam of radiation is emitted along the magnetic axis of the pulsar, which spins with its rotation. So it's very much like a lighthouse that you would see spinning around, and you'd see this beam every time the lighthouse's light would pass you. The magnetic axis of the pulsar determines the direction of the electromagnetic beam. And this rotation does slow down over time after 10 to 100 million years. So we don't really notice that kind of spin down, but the pulsar does eventually turn off.
Sorry, that's just a quick question.
Absolutely.
Does this mean the magnetic axis and the axis of rotation are different?
The question was, does this mean the magnetic axis and the axis of rotation are different? They are.
Cool.
Absolutely. So here we have a very illustrative diagram. So this is an artist's rendition, obviously, of a pulsar, since we can't really get to them. So you have the pulsar in the center, and then you have the electromagnetic waves that are emanating from the pulsar. And then you can see the rotation axis going up and down like this, and then the axis of the emission, which is aligned with the magnetic axis going at that angle. So we actually have different kinds of pulsars. And the ones that are particularly interesting for gravitational wave astronomy are something called millisecond pulsars. Why? They are the universe's most reliable and most precise clocks, even more precise than atomic clocks. They have an incredibly stable rotational period between 1 and 10 milliseconds. Again, about the same rate as your kitchen blender, which is pretty staggering if you think about it. They also have been detected all across different spectrums, including in the X-ray, radio, and gamma ray portions of the electromagnetic spectrum. However, we don't really know how these are formed. The origin of these is fairly speculative at the moment. The leading theory is that they begin life as longer rotation pulsars, but are made to spin faster through a process of accretion. And accretion is a big word, so I have a picture on the next slide. So imagine, if you will, accretion as a cotton candy machine. And you have that little cone for the cotton candy. Imagine the cone as the pulsar. And so you're spinning it. Paul is laughing at me again. You spin it around, and as they both spin around, you collect more and more cotton candy from the sides. Imagine the cotton candy as mass. So. Oh, okay. Oh, man. Well, the important thing is you all knew what I meant, right? Okay, so here's a picture of how we think neutron star accretion works. So you have the neutron star in the center, and usually, this is what we're thinking, millisecond pulsars are created in a binary star system, where you have the neutron star, and then you have a much larger radius star that it's kind of sucking the life force from, as it builds its own rotation speed up to millisecond proportions. So There are many international organizations who are pursuing the detection of gravitational waves. This is kind of a big deal in the frontier of cosmology. You may have heard of LIGO and the Square Kilometre Array, for example. Yeah. Okay, fine. They are all partners in our International Pulsar Timing Array collaboration. My lab works for a group called NanoGrav, the North American Nanohertz Observatory for Gravitational Waves. It's just easier to say NanoGrav. And it is indeed a consortium of astronomers who try to detect gravitational waves using a millisecond pulsar timing array. So our particular strategy for gravitational wave detection is to use a galactic network of millisecond pulsars to create a kind of web to catch these waves. So remember this pond that we were imagining a couple minutes ago? Now imagine casting a fishing net over the surface of the water. And you're holding on to the end of the fishing net so you can tell what's going on. The lines of the net are like the radio emissions from the millisecond pulsars. And the places where the lines in the net intersect are where you would find the millisecond pulsars themselves. If something causes the surface of the lake to ripple, the net's going to blip too. The net will ripple in accordance with the ripples that are happening on the surface of the water. So our goal is to eventually create an array of millisecond pulsars that are so precisely timed, I'm talking like 9 significant digits, so precisely timed and clearly timed that we can detect those blips caused by gravitational waves by monitoring the radio emissions from those millisecond pulsars. So what do we do at the Oberlin Pulsar Lab? What contribution does my lab make to this effort? So imagine us as the guys who are trying to skim all the junk off the surface of the lake, trying to get all the twigs and all the leaves off of the lake. So all we have is the fabric of space-time, the gravitational ripples, and our array. We study the interstellar medium, which is the stuff between us and the pulsar, so we can filter it out and just get the pure radio signal from the star. So the radiation from pulsars passes through the ISM on its way towards us. And because of the dispersive nature of interstellar plasma, lower frequency radio waves travel through the medium slower than higher frequency radio waves. So this causes a delay, and the resulting delay in the arrival of pulses is directly measurable as the dispersion measure of the pulsar. Now if we had a board, I could do some calculus and show you how we calculate dispersion measure, but that's not necessary. The important part is that turbulence in interstellar gas also causes denser spots in the interstellar medium. So it's not a homogeneous mixture of gas. You have these little pockets of really super dense gas in between us and the pulsar. And those serve to scatter the radio waves that we get from the pulsar. So the resulting scintillation of the radio waves, it's very analogous to the reason stars twinkle, or the reason we think stars twinkle, because of the inhomogeneity of our Earth's atmosphere. These scintillations can actually be used to map the interstellar medium so that we can filter out all of the stuff that is clouding up our signal. So how do we do this? All of this incredible work wouldn't be possible without some very powerful tools. I came to this project because the research is pretty interesting, and I think everybody in the room would agree at this point. It's pretty awesome research. So if you know me at all, you can discover my delight. You can imagine my delight when I discovered that the tools that form the basis of our work are indeed open source. Yay. All right, Presto. Presto is a tool written by Scott Ransom, who is a Debian user, coincidentally, who is a physicist with the National Radio Astronomy Observatory and one of the main contributors to NanoGrav. So this program was first designed to search through radio data, kind of combing the radio data from telescopes like Parkes to find the signals from pulsars. A significant portion of the code is written in C, but most recently the functionality that has been added in the past couple of years has been written in Python. So it's kind of this Frankenstein monster of C and Python that's all kind of jumbled together, but it manages to do some pretty incredible things. And as a testament to the effectiveness of this code, we've found more than 150 pulsars with it so far. So, I don't need to explain to you all why we should choose open source. You wouldn't be here if you hadn't already made that choice. But something that's easy to forget is that many people in organizations, especially in the academic community, for them, that choice isn't as obvious. And the fact that Scott chose to make his code open means that everyone in this room, and everyone in LCA, and everyone else that eventually sees the slide deck can get a copy of Presto on their machine and start looking for pulsars themselves. Okay, so here's how. I've outlined the steps. I don't feel like talking through the code because that's kind of boring and dull. These slides will absolutely be available, so if this is something you would like to do, yes?
How well does it scale sideways?
How well does it scale sideways? I have no idea. I am a Debian user, so Debian is the only distribution I've tried it on. I suspect that it would scale pretty well, but I don't have a solid answer for that question. Yeah. So it's available from GitHub. The one thing that is important to know if you decide you want to try this for yourself, and we're going to walk through the steps in a couple minutes, is you will need at least a gig of free disk space. Performance of the disk is really important. Otherwise, this work is going to be really slow and really tedious, and it's going to take hours, and you're just going to sit at it staring. It's like, I want to be on lolcats. I don't want to be working on this anymore. So doing it in /dev/shm, it may improve your performance. I mean, especially if you're using an SSD, doing it all in temporary memory would be great. But if not, make sure you've got a gig of free disk space so it doesn't totally eat your computer. All right, and there is a sample data set available for you on the web. So if this is something you would like to do, again, pull these slides later so you can actually get step-by-step stuff with URLs. All right, so I'm going to go through a very basic outline of how we use Presto to search for pulsars. Obviously, there's a whole lot more involved in this. First, we examine the data format. This is just a read file. This is just, all right, so what kind of data are we dealing with? And then we search for RFI, which is radio frequency interference. That's a huge problem for us in finding pulsars because it often creates false positives. So one of the first things we want to make sure we do is screen out all the RFI. And then we make a topocentric dispersion measure of 0 time series. And those are the commands to do it. So topocentric means Earth is at the center. Barycentric means that the sun is the center. So topocentric is what we want because all of our data is collected obviously from the Earth. So we want to make sure we've put our axes in the right place, so to speak. And dispersion measure, we were talking about that earlier. Dispersion measure of 0 means that we're not trying to track any delays due to the interstellar medium. We are assuming that there's nothing between us and the pulsar. Now that sounds like kind of a dangerous assumption to make, but when we are just in the process of looking for pulsars, we can kind of get away with that. Once we start actually analyzing data from pulsars that we found, that's when it becomes important to screen out all the stuff between us and the pulsar. And then we take the real part of the fast Fourier transform of the time series, so we get from time space into frequency space. Then we go through and identify the birdies, that's what we call them, to zap in the searches, and those are the things that are brought up by radio frequency interference most often. And find things that in the data that clearly aren't pulsars. So this is a first level screening mechanism to be dealing with the least amount of data possible. Then we make a dedispersion plan and we dedisperse. And then we search the data for periodic signals. Now, question for the audience. Why are we searching for periodic signals? Yes, that was the correct answer. Yeah, so we're searching for periodic signals, obviously. So we will search the data for single pulses. We're not looking for binary pulsar systems at this point. We're just looking for single pulses, make things really simple. And then we're going to sift through the candidates that we found. And then we're going to fold the best candidates back from frequency space into time space. And then we're going to start timing the new pulsar. And if this is at all interesting to you, which it should be, a more detailed tutorial can be found at that URL down there. Scott has put together an incredibly thorough 80 pages worth of step-by-step. These are the commands that you're going to need. These are the windows you're going to see. It's fantastic. I actually did this summer in summer school. One day of this little intensive summer school that I had was playing with Presto and actually finding pulsars. And I can tell you from firsthand experience, it's pretty gratifying. So another really powerful software suite that we use is called Tempo. And there's a newer version called Tempo 2. So Presto is more about finding the pulsars, and Tempo is more about timing them. Because for our research, being able to very precisely time the pulsar is critical. So Tempo, obviously another program for the analysis of pulsar timing data. And there's a lot of words on these slides, and I didn't realize that when I went through this. So you can obviously read those for yourself. But the thing that is most important about Tempo is it has a series of models built into it. And rather than try and start from scratch, build from the ground up when you're timing the pulsars, you're using a model and trying. It's like a best fit. It's absolutely like a line of best fit. I mean, at the most simplistic example, you have a set of models that you're trying to fit your pulsar data to. And once you've found something that's really close, then you can do one of those macro to micro kind of zoom in, and then you can really start fitting your data to a timing series that will help you work with precision. So we have the most important types of Tempo output files. Tempo would be more difficult to try and use on your own because it's much more finicky than Presto is. So Presto is really the place to start if you want to start doing this for yourself. If you decide that you actually want to time the pulsars, come find me or shoot me an email, and I would be happy to either help you myself or set you in the right direction. I had a much harder time with Tempo than I did with Presto because there's this strange little user interface where you have this signal and you have to like click things and drag things to try and form it to a model, and that was a lot harder than, and Dad's gonna laugh at me, it was a lot harder than just running the commands in the terminal for Presto. So, yeah, so as you can see from this slide, you start with a tempo file format, and it lists all sorts of data that you're going to need to fit, and then you end up spending the rest of your time looking for residuals, doing the how good of a fit is this really, and how useful would it be, and do I need to go look for another model to try and fit this data to? So that's Tempo 2. So we're going to enter the personal anecdote portion of the talk, and this is entitled Summer Adventures in Code Translation. So I was part of a group this past summer that was asked to help in a code translation project. One of our collaborators, who was working at the time on his PhD thesis with an association with Cornell University, he's actually at the University of Sydney, but he was getting his PhD at Cornell, wrote a great piece of code that builds on our previous code and methodology and software that helped us study the interstellar medium. For this project, he decided to write his code in C, which is, as we all know, very robust and very reliable and a great place to start. However, the Nanograv collaboration has slowly started moving all of our coding efforts into Python. And so, despite the protests of certain people in this room, we decided to translate this chunk of code from C into Python, which sounds backwards to some people, but it's what we needed. So, being the kind of person I am, I asked my professor what kind of revision control system we used in the lab, because, yeah, you can see where this is going. What is this? So, this turned into my summer adventures in revision control. So the lesson we learn here, children, is that be careful what questions you ask, because you could end up being the person who comes up with the answer. So after volunteering to set up the revision control system for the lab, I started by making a list of the things that I thought we were going to need. Git seemed like the right answer, because the members of the team who were involved in this project were going to be very widely geographically distributed, all needing to collaborate on the same piece of code. And we needed to preserve the privacy of Ryan's code. Now, preserving code privacy at this conference may sound a little counterintuitive, But what we sometimes fail to remember in the academic community is that these people's careers, their livelihoods, and their reputations are built on being able to have access and sole control over this code. Especially for Ryan. I mean, this was his PhD thesis. He'd been working on it for 7 or 8 years by this point. If his code had been open sourced, he most likely would not have been able to defend his PhD thesis, and he would have had to start from scratch because this code needed to be his until he got the PhD. And after he got his PhD, I have not been in touch with him recently, but it has been suggested to him that it would be great if he would open source his code afterwards, but that's his decision. It wasn't our code. We were asked to help with somebody else's project. Yeah, it would have been devastating. So after thinking about all these different things, needing an interesting configuration of permission controls to make sure all the members of the team felt like they were equal contributors and nobody else was stepping on each other's toes and messing up each other's code. Yeah, it seemed like the right answer. The very helpful Nanograv sysadmin suggested Gitolite, which I had not heard of. Just curious, how many of you have heard of and or used Gitolite? Awesome. Awesome. Oh, fantastic, fantastic. Well, for good reason. So Gitolite, it's very much like GitHub, except it's not a cloud, web-based, ephemeral, you push your code to somewhere and you can see it on a web browser. Gitolite allows you to set up Git hosting on a central server, which was critical for us being so widely geographically distributed. The biggest difference between just straight Git and Gitolite is the fine-grained permission controls you can implement. You can be very particular about who has access to what, who has read access to what, who has write access to what, and those two don't have to be joined together. They can be mutually exclusive, which was really important for this project. You use a single Unix user, the real user on the server. That was me, since I was setting it all up. You provide access to many Gitolite users. Another important thing is they don't get shell access. So they can't really screw it up too terribly much. And this Gitolite is kind of an umbrella thing that allows you to control access to many Git repositories, which was going to be useful once we had finished the translation project and had started implementing the code. If we were finding bugs, once we had a master copy of the Python code, we could fork off another repository and have the same permission structure work with that too. That was very important. The write access was controlled at the branch tag file directory level, including who can rewind, which was really important because we're all learning how to code in Python at this point, create and delete branches. It can be installed without root access, which meant that I could have hosting for our Gitolite repository on a supercomputer in the chem lab at my university. And I didn't have to have root access on that machine to do it. I would never have been able to get permission to have our repository on a supercomputer in the chem lab if I had needed root access. And then, yeah, authentication, usually use SSHD, but you can also use HTTPD if you prefer. That may require root access. So we did it with SSHD and had no problems. So, some more code. Again, if this is interesting to someone who has not set up a Gitolite repository before, I would strongly suggest coming and finding these slides later and actually going through them line by line. I ended up writing a how to use Git with a how to use Gitolite manual for the lab once I had finished this project, because it took me a long time to figure all this out. So I'd never heard of Gitolite before, so I was learning this at the same time I was learning C and Python to be able to work on this project. So I wanted to make sure that everyone else in the lab had a very clear page of what exactly to do to make sure that they could get on with the work and not have to be mired in all the line-by-line problems. So here, line by line, it's how you set up Gitolite. And then, yeah, so one thing that was really important that you had to keep track of was which machine you were on. Because there is a lot, actually, I'll go to the next slide. There's a lot actually going back and forth between the machine where your repository is hosted, and the machine that you, as the super user of the repository, are using to set up the permissions. And if you set up the permissions on the server where your central repository is located, it can screw all sorts of things up. So I had to go through a couple iterations, actually, of making sure that I was on the right machine doing these specific steps. So there's actually a Gravitational file, which took, again, it took a long time to figure out. I would think I was doing it right, and then I'd realize I was missing a space, and then I had to go back and edit it. But this, as it is now, is the way it should look. And the R is read, the write is, well, the W is write, obviously. And then the plus means that you can read and write on all the branches, not just your own. Yeah, there's only one person who could do that in the repository. And then the other members of my team, D. Steinbring, J. Nelson, Josie N. Nelson, they had read and write permissions on their own branches. That's what this section of the conf file is all about. Making sure that D. Steinbring had read and write permissions on the branch D. Steinbring, and not on anybody else's branch. And then, yeah, at the end, git commit, git push. If you don't push it, it doesn't exist. So done with admin things for now. And then this was the last piece, creating a directory for your project. So as you can see, Brism was the name of our code translation project, and sa279sc.csr.oberlin.edu was the secure stack in the chem lab that we were so graciously given space on. Yeah, and then git k-all, so you could actually look and make sure that it was what you were expecting when you were doing all this weird configgy stuff in a terminal. And then you create a README to seed your repo with, just something to get you started. We didn't actually get to the point where we were using this summer. So I was thinking maybe I would seed the repo with a full copy of Brism in C instead of a README, because I thought maybe that would be a better use of the space, but it ended up with time considerations and people's travel schedules and whatnot. I just ended up seeding it with a README, so we could add code later as we saw fit. Yeah, check out and push. So why don't you have a master branch? Yeah. When I created our repository for this translation project, I unconventionally created it without a master branch, and this was a decision that took a lot of thought, a lot of head scratching. So in the end, I decided not to have a master branch for this reason. We were all collaborators. All of us, including our professor, were learning C and Python in this weird thing called Git together, and that meant that none of us were experts. And the way I set it up, without the master branch, meant that each of us would be able to check out a full copy of the C code onto our branches, work on the different parts of the code that we had decided we were going to tackle that day, preserving our individual contributions within the collaboration. And as I explained to you a minute ago, each of us could see everyone else's work and build on it, but I felt the collaboration was best served by not having a master branch. So that brings in this whole question of collaboration versus competition, which everyone in this audience is intimately familiar with. So at the summer school I attended this summer, the last talk of the conference was a discussion of how all the international members of this grand pulsar timing array would deal with authorship on the paper. The paper that we publish when we actually find a gravitational wave, the paper that will win the collaboration and Nobel Prize, because that's the magnitude of the stuff we're working on. How are we going to deal with authorship? And as I listened, this discussion started sounding eerily familiar. This whole balancing act between collaboration and competition is something that we deal with very personally in the open source community. So I'm sure all of this is pretty self-explanatory, but I mean, with collaboration, you've got shared resources. In our case, that means we're more likely to actually find the pulsars because we have more people looking for them. We have shared goals, and everyone in the collaboration gets credit which is very important in the publish or die academic community. I mean, if you do work, you need to get credit for it in order to further your career and make sure that you have more opportunities down the road. But then again, you've got competition, which encourages continual betterment to ensure you can actually compete, to ensure that you have something to offer that no one else does, which makes you very important and very desirable for collaboration in a community. You've obviously got fewer management headaches with fewer people involved. That's huge. And fewer people have to share the credit, especially on something like a paper that's going to be submitted to the Nobel Committee. It would be kind of awesome if you were one of 2 people on the paper instead of one of 86. I mean, it's a little arrogant and a little egocentric, but it is true that in competition, fewer people have to share the credit. And credit, unfortunately, does often directly translate to funding. So I would like to leave you with a quote from one of my personal heroes, Carl Sagan. So if collaboration is so difficult, why do both the astrophysics and open source communities keep using it as their working model? Well, the more likely we are to assume that the solution comes from the outside, the less likely we are to solve our problems ourselves. We can judge our progress by the courage of our questions and the depth of our answers. And I think that is best served in the open source community and the astrophysics community by this collaboration that allows me to come and speak to you about it at a conference that normally wouldn't see something like a sexy science astrophysics talk. And I feel very privileged to have been able to bring the collaboration down under. And yeah, so thank you.
You must have lots of questions now. Where do we start?
So, is that on?
Yeah, it's on.
So you said that you were working with LEGO in UWA,
Yes.
but all of your stuff seems to be radio astronomy based.
Yeah, so we have a big umbrella collaboration / competition with other organizations that are trying to detect gravitational waves differently. LIGO isn't using pulsars.
No, they're
interferometry. Yeah, exactly, interferometry. And it's kind of a friendly race to see who finds them first. Because to be honest, at the rate our research is moving, it might actually be the next 5 to 10 years that we detect the first gravitational wave. So LIGO obviously doesn't use the methodology and the software and the pulsars and the stuff that we use, but yeah, it's a friendly competition atmosphere with things like LIGO and the SK.
Well, anyway, I guess interferometry and pulsar timing provide a good sort of cross-check with each other anyway.
Absolutely.
Yeah.
Absolutely.
Also, to get to my question, as a computational physicist, how often do you find that you have to deal with nasty old legacy Fortran?
So yes, yeah. I myself have not encountered the proverbial nasty chunk of Fortran code. However, before Nanograv started moving most of its software development to Python, we were using IDL. And I don't know if any of you are familiar with IDL. It's something that you get to pay for. And it's something that's kind of like Python, but not enough like Python to actually be useful. So I actually had a really awesome animation that I wrote for the lab describing this whole space between us and the pulsar with the interstellar medium and all the stuff that gets in the way. Animation that I wrote in IDL, and my license expired a couple months ago. So I get 7 minutes of IDL at a time. And those 7 minutes were not enough for me to remember how to call up the animation, so I had to put a couple extra pictures in. No, so I have not run into the chunk of Fortran code, but IDL is kind of close.
Just on Get-A-Light, did you? There's a feature in Get-A-Light for actual personal branch namespaces, so you can actually just say all these users
Oh, wow.
can have their own namespace that they can commit any branch they like into.
That's fantastic.
Yeah. It's totally
Wow.
awesome.
That's pretty awesome. Thank you
I
for
thought
that.
that might be a neat,
Oh, absolutely. No. So unfortunately, this semester has been really crazy at school for all of us in the lab, including my professor. He's actually teaching 2 classes and the head of the physics department and a researcher and outreach/recruiting. So we haven't actually started the translation project yet. I decided that my time would best be served by setting up the infrastructure this summer. And then once we got the infrastructure set up, school started. And once school started, it was like, problem set, learn how to code. I know for some of you, those 2 might not have been mutually exclusive, but for me at least, it was one of those, well, I should probably get my homework done first. So once we actually start using the repository and start doing the translation project, I will absolutely read up somewhere on Get a Light, because that sounds fantastic.
Two things. First of all, I saw today that apparently someone's just found a new fast Fourier transform algorithm that's about an order of magnitude faster in many cases.
Really?
So that might help speed Presto up, which you said is sometimes a bit like watching paint dry.
Absolutely. Yeah.
That sounds good. But I actually wanted to ask, you mentioned that you had a sample data set there.
Yes.
Presumably there's some way that if you get into it, you can actually pull down chunks of real data to do more. Or
Yeah. That's the point. I am not intimately familiar with our policy on sharing our data that we as a collaboration collect, but that is definitely something I will look into, because I mean, once you've tried it once, you're going to want to do more. Yeah, it's dangerous. No, so I will absolutely look into how our permission structure works for our data, and hopefully you could do some more.
Have you considered using GPUs to speed up your processing?
Yeah. Well, that comment might have been misleading. In the summer school, working with Presto, it did take an afternoon, but not because I had issued a command and was waiting for it to do what I had asked it to do. It was the put a command up on the slide, go around to all the students, make sure everybody's getting what they need, and then go to the next one. So I have myself not actually tried doing the Presto search and the Presto timing independent of that one-on-one, making sure everybody's got what they need setting. So it might actually not be as slow as I am familiar with. It might actually be a lot faster, but no, that's a good suggestion. Absolutely. Yeah.
Slightly trivial question, but
I'm down with odd questions.
if the machine that you're running Presto on happens to find a pulsar, do you get to name it?
I suspect you might have a vote. So the sample data set, I will give you all a huge hint. The sample data set actually has a pulsar in it. We won't just be sending you on a wild goose chase. So this data that is available via the URL does actually have a pulsar in it. No, but if you do end up discovering a pulsar on your own, I suspect we could reach an agreement. You could talk to somebody. You might have to share the credit. Actually, pulsar naming isn't by name. Pulsar naming has to do with where it is in the night sky. So right ascension and declination are how we name our pulsars. So that is the appropriate response. Yes, you would. I think your best option would be to change your name for sure.
Or name the region first.
PS plus 159. Yeah.
I live in Wellington, and I was just curious to know when that became a unit of measure.
I didn't hear the question.
I live in Wellington. I was just curious to know when that became a unit of measure.
Oh, I have no idea. I haven't been to Wellington in a long time.
So you want to put Wellington into a blender?
Well, I mean, Wellington's a nice place, but I haven't been there in a while, so it could have changed since I was there. Big Auckland. No. No, but it is really amazing to think about something as pedestrian as a kitchen blender. I mean, that thing spins really fast. And something much more massive, and when I say much more massive, I literally mean supermassive. A supermassive star spinning at that. It just blows your mind. If you think about it too long, you'll get stuck in this feedback loop and your eyes will glaze over and won't be able to think about anything else.
Is it on?
Yeah.
Okay. One of your early slides, where you were talking about gravity waves.
Yes.
You said there's been no direct observation of
Yes.
gravity waves, but there was evidence that they existed. What's the evidence?
So if you think about the surface of the lake again, and you think about the ripples, if there is something else on the lake and the ripples reach it, it's going to move, or it's going to react in some way. I mean, much like the wind, we don't see it, but we know it's there because of its effect on its surroundings. That's how we suspect that gravitational waves exist, because we think we see their effects on bodies that we can actually measure. But again, we don't have any direct proof. And so that's what this whole initiative is, trying to directly detect the waves themselves, not just their effects on the surroundings.
But Einstein's theory predicts these things.
Yes, Einstein's theory of general relativity does postulate gravitational waves. So, I mean, if you think about it, we haven't really proven Einstein's theory of general relativity yet either. So, if you want to sound really important when you're talking to somebody about your work in an elevator or something, you say, well, my work will directly prove Einstein's theory of general relativity, which up till now has just been a theory. And you can sound really important and pompous, and then explain to them that it's, you understand.
Any more questions? Nope. Well, Elizabeth, we have a gift for you.
Oh, thank you.
On behalf of the Linux conference today, I'd like to present you with a little glass and gold penguin.
I'm so excited.
So, thank you very much.